Okay, Ropke here. This is 2I rational functions, and I got to start this off by disagreeing with the textbook. They're claiming that any rational function that we're going to consider in this course can be written in this form here, where it's just a linear function divided by a linear function. This is just not true. Okay, we're going to see lots of other rational functions in this course. I don't like this definition at all. Just a quick Google will tell you that a rational function is actually a quotient of two polynomials. So what we see here is an example of a rational function. It is a quotient of two polynomials, but they do not need to be linear. Okay, so that's a big point I got to make here right off the bat. This particular type of rational function, it's true, it will have asymptotes, which are horizontal and vertical lines, but that is not true of all rational functions. Rational functions do not necessarily have to have asymptotes at all, and they don't need to be horizontal and vertical lines. The asymptotes that we consider in this course will be horizontal or vertical. That I can promise you. Now, all of the rational functions in this particular section will be a linear divided by a linear, and you'll see this type a lot throughout the next 2 years. So let's learn a little bit about them. Let's look at a very simple one first, and then we'll get more complicated as we go on. So here's the simplest rational function that there is really is 1 over x. That's technically, that's a quotient of polynomials, I guess. The denominator certainly is a polynomial anyhow. It's a boring one. Now they call this a rectangular hyperbola, this graph that we see here. We definitely don't need to know that word rectangular. However, the word hyperbola, I've already used it in previous videos. We'll be using it a lot. It's anything that's going to have this basic shape, like this, or it could be flipped over like that. The ones that we see, as I said, are going to have vertical and horizontal asymptotes, although technically you could draw a hyperbola that's rotated in sort of any way at all. So this particular one, it's got 2 branches. So does every single hyperbola. This particular one is undefined when x equals 0. That's very obvious from the function rule itself. But that's not going to be true for every hyperbola, certainly not. This particular hyperbola is only in the first and third quadrants, but hyperbolas could be translated up, down, left, and right, and in fact, you could draw a hyperbola that exists in all 4 quadrants, so that's not a particularly interesting point to make here. This one happens to be symmetric about the line y equals x, and that's interesting if we're thinking about this in terms of inverses, but that's for the next section. I'm not going to discuss that here. We can talk about what's called the end behavior of this function. I believe I've talked about this before. As x gets really, really big, as x gets closer to infinity, the y value gets closer to 0. Now they say the words from above. If I was writing this, I would just write y approaches 0 from above. You can use a plus to indicate that. And likewise here, to say that as x approaches negative infinity, we're getting closer and closer to 0 from below, I would just write y is approaching 0 from the negative direction. And same idea for these two. I would write that as a plus and a minus. So here's a more interesting example, 2x plus 1 over x minus 1. And I've got a picture of the graph here, but let's see how much of this we could figure out on our own just by thinking about this algebraically. So first of all, I notice that this function is going to be undefined when x is equal to 1. So that would enable me to draw in a vertical asymptote. And the next thing I would check is, when is this function going to be equal to 0? Well, that's going to be when x is negative 1/2. And I'd also check out, that's an x-intercept, so how about a y-intercept? Well, when x is equal to 0, clearly my y value is going to be negative 1. The next thing I'd want to work out is where the horizontal asymptote is. So I'm going to show you a little shortcut for how to do this. Basically, the trick is you've just got to look at the leading terms, and specifically their coefficients. The coefficient on the numerator divided by the denominator, that's just 2 divided by 1. That's your horizontal asymptote. It's 2. And the reason for this, I'm kind of thinking using some calculus ideas here, but basically, if I choose a number that's super, super, super big, so I'm looking way out here as x goes to infinity, a super big number, when I multiply it by 2, I still have a super, super big number. The fact that I'm adding 1 doesn't really change that. Likewise, in the denominator, when I take a super, super big number and then I subtract 1 from it, the subtracting of 1 really doesn't change it very much at all. So we can kind of ignore these terms. We just need to think about what the absolute biggest terms are, and that gives us a pretty good idea of what the y value should be. If you're uncomfortable with this, let me know. We can talk it out in person, but it's a neat trick, and it absolutely works in all cases. It'll even work when we don't have linear functions, and we'll see examples of that later on when it's time. But for rational functions that we're looking at here, it's always going to be linear, and the horizontal asymptote will always be the ratio of the coefficients of the x terms. Now really, once I have the axis intercepts and the asymptotes, I'm kind of done. I don't really need to do a sign diagram, but might as well, just to make sure we know what the y values, how the y values should be behaving. The reason I don't really need that is, let's just imagine this. So let's say I have my axes here. I have the asymptotes, and I know that it goes through those 2 points. Since I know that I'm dealing with a hyperbola, either it's going to be in the top right part and the bottom left part, which would make sense here, or it's going to be in the top left and the bottom right. But if it was in that case, then it wouldn't have gone through the 2 points that I know it needs to go through. So really, my sketch is done already. But I like looking at a sign diagram just to make sure that my work is definitely correct. The sign diagram will tell us right away where the y values need to be positive or negative, and that certainly matches the graph that we're given. So here, let's start off with letter B, because letter B is not written in the form that we're used to at this point. So we're just going to make that form happen, okay? We're going to just combine these two. So this is going to be 2 times x plus 1 minus 3 over x plus 1. And that'll be 2x plus 2 but minus 3 divided by x plus 1. So now if I want to graph this, I need to think, okay, what are my asymptotes? And what are my axis intercepts? Well, my vertical asymptote is going to be x equaling to negative 1. My horizontal asymptote, that's going to be, again, just like the previous example, it's going to be 2 divided by 1, which is 2. My y-intercept, if x is equal to 0, my y-intercept is going to be y equals negative 1, again. And my x-intercept is going to be, in this case, when 2x minus 1 is equal to 0, this is going to be x equals positive 1/2. So let's start graphing this. There's my axes. I know that my vertical asymptote should be to the left of the y-axis. My horizontal asymptote should be above the x-axis. I've got a y-intercept down here. I've got an x-intercept over here. So pretty clearly my picture should look something like this. It's a wonderful graph. What did we leave out here? Oh, okay, so it said to state the domain and range. I suppose I could have done that from right here. Since the vertical asymptote is x is equal to negative 1, that means that the domain should be x is not equal to negative 1. And the range, similar, should be y is not equal to 2. So finding the domain and range is equivalent in this case to finding the horizontal and vertical asymptotes. So that's easy. I already found the axis intercepts. Oh, discuss the behavior of the function. So if I want to discuss this behavior, I'm going to say as x goes to infinity, y is approaching, horizontal asymptote is 2 from below. As x approaches negative infinity, y is going to approach 2 from above. As x approaches, my vertical asymptote is negative 1 from the left. Y is going to approach infinity. And as x approaches negative 1 from the right, y will approach negative infinity. So there you go. That's everything there for letter B. I think that's all that I'll say about that. The other examples are all in the correct form, so we don't have to do any extra steps in the beginning. That's rational functions for you.